In this video, we look at hypergeometric distribution. It has three parameters: cap n, small n, and small m. So consider an urn. An urn containing a total of cap n balls. M of them are blue, and so the remaining cap n minus m are red. Let's pick small n balls without replacement from the urn. Then the sample space S will be the set of sequences of n selected balls from the urn. Assuming that that order is not relevant, then the number of sequences of n balls selected from an urn containing a total of cap n balls would be given by the binomial coefficient cap n choose n. Okay, once again, the number of sequences of small n balls selected from an urn containing a total of cap n balls is the binomial coefficient cap n choose small n. Let's let x be the number of blue balls selected. So we are picking a sample of small n balls, and x is the number of blue balls in the sample. The question then is, what is the number of ways we can pick n balls where k of the balls are blue and n minus k of them are red? Well, in order to answer that, what we find is, first of all, how many ways can I pick k blue balls from the urn? Well, there are m blue balls in the urn, and we want to pick k of them. So there are m choose k blue balls that can be picked for the sample. Now, how many ways can we pick n minus k red balls from the urn? Well, there are capital N minus m red balls, and we want to choose small n minus k red balls. And so the number of ways we can pick n minus k red balls from cap n minus m red balls is n minus m choose n minus k. So by the multiplication principle, the number of ways we can pick n balls from the urn with k blue balls and therefore n minus k red balls is m choose k times n minus m choose n minus k. So once again, the number of samples of n balls that can be picked from the urn where there are k blue balls and n minus k red balls in the sample is given by this product. So hence the probability that x is k, that is the probability that there are k blue balls in a sample of small n balls taken from the urn, is given by m choose k times n minus m choose n minus k divided by cap n choose small n. So this is the probability. This is the PMF, probability mass function of the variable x. The variable x here is called a hypergeometric random variable, and its distribution is called the hypergeometric distribution. Now the expectation of x turns out to be n times p, and the variance of x turns out to be np times 1 minus p times 1 minus n minus 1 over cap n minus 1, where p is m divided by cap n. Okay, so next what I want to do is show you how to derive the expectation of x. In order to derive the expectation of x, I want to start out by making a remark. Notice that the binomial coefficient cap n choose small n is cap n factorial over small n factorial times cap n minus small n factorial, and cap n factorial can be written as cap n times cap n minus 1 factorial, and small n factorial can be written as small n times small n minus 1 factorial. And if we do that, notice that we can rewrite n cap n choose small n as cap n divided by n times cap n minus 1 choose small n minus 1. So far we have cap n. So far we have cap n choose small n is equal to cap n divided by n times cap n minus 1 divided by small n minus 1. We can multiply both sides by small n, and we derive that small n times cap n choose small n is cap n times cap n minus 1 choose small n minus 1. In a similar way, we can also derive that I times m choose I is the same as m times m minus 1 choose I minus 1. The derivation is exactly the same because these two identities are exactly the same, except that we are using different symbols in the two identities. Alright, so let's now start to derive the expectation of x. So the expectation of x is, by definition, we sum over all values of x, and so let's say sum I going from 0 to n. The reason is x is the number of blue balls, and we are picking small n balls, so the maximum number of blue balls would be small n. So now we multiply I with the probability of I. Now this is equal to the summation I going from 0 to n, and we know that P of I would be given by this. In fact, instead of using I, let me use K to match what I had in my PMF. So let's use K here. K going from 0 to n, P of K, K times that. This is K going from 0 to n, K, and P of K we know is m choose K times cap n minus m choose n minus k divided by cap n choose n. Okay, so this is what we get after we plug in the PMF function. Now what we're going to do is the following. This is the same as the summation k going from 0 to n, and what we are going to do is we are going to replace the denominator cap n choose n by using this identity here. So if we use that identity, what we will be, and also we are going to use well, basically we're going to use these two identities here for m choose k and for cap n choose n. So if we do that, okay, so let me write this identity by using k so that it's clear. So if I use k, this is what I get. So if I we can replace k times m choose k by m times m minus 1 choose k minus 1. So let me write that down. M times m minus 1 choose k minus 1. I still have n minus m choose n minus k, and in the denominator n choose n would be cap n divided by n times cap n divided by n times cap n minus 1 choose n minus 1. Okay, so we're going to do a little bit of algebra now. So altogether I'm going to get m n divided by n summation k going from 0 to n, m minus 1 choose k minus 1, n minus m choose n minus k divided by n minus 1 choose small n minus 1. Okay. Notice that when k is 0, notice that in this sum, when k is 0, we get a 0 term in the sum. The term corresponding to k equals to 0 is 0. So I could then start the sum at 1. So 1 here, 1 here, and 1 here. Okay. Then I am going to write this as mn divided by cap n, and I'm going to replace k by k plus 1. If I replace k by k plus 1, then the index is going to go from 0 to n. So replace k by k plus 1, I'm going to get m minus 1 choose k, cap n minus m choose n minus when you replace k by k plus 1, you get n minus k minus 1 here divided by cap n minus 1 n minus 1 here. Okay, so notice now so now we have to observe something here. What we want to observe now is the following. So we're going to rewrite this, the summation k going from 0 to n, m minus 1 choose k. Here what I'm going to do is, okay, so the denominator here is cap n minus 1 choose n minus 1, and here I'm going to rewrite this as cap n minus 1 cap n minus 1 minus m minus 1, which is still cap n minus m, choose n minus k, n minus 1 minus k. Okay, so I have this binomial coefficient here. The reason I rewrote in this way is the following. If you think about this ratio here, if I define a variable y, let's define a variable y to be the number of blue balls in a sample of size n minus 1 taken from an urn containing a total of capital N minus 1 balls with m minus 1 blue balls. So what I'm saying, think about having a urn where you have a total of cap n minus 1 balls and m minus 1 of them are blue and cap n minus m of them are red. Okay, so if you subtract cap n minus 1, if you subtract m minus 1 from cap n minus 1, you get n minus m. So if y is the number of blue balls, then this ratio in the sum here is this ratio in this inside the sum here is the probability that y is equal to k. So this sum is the sum of the probabilities of all the values of y which is then the total probability of y, which then should be simply 1. So that sum is 1, so that means I get mn divided by n times 1, which is mn over cap n, and hence the expectation of x is mn divided by cap n, which I can write as n times p, where p is m over n, which is what I wanted to derive. So this is how we can derive the expectation of x. The variance of x can also be derived in a similar way, so I'm not going to go over that. So this ends the discussion on the hypergeometric distribution. In the next video we will look at the Poisson distribution.